In chapter 9, we're starting to talk about solution chemistry. And solutions are so important because most reactions are going to take place in solution. It's what enables, once your chemicals are dissolved, it's what enables the different parts of the chemicals to mix around and come in contact with each other. And so a solution is a great place for a reaction to take place. So the first place that we need to start is determining actually how a solution happens in the first place. How does the process of dissolving actually happen? Well, if I take the very simple solution, a saltwater solution, and he does have some diagrams of this in your book where the pictures are probably a little bit more realistic as far as atom size. Maybe it's because I'm getting old and I need glasses now, but sometimes I find those diagrams with some of the atoms bigger than others, I find them a little harder to interpret. So I'm going to show it to you a little bit different way here, so hopefully you can understand the mechanism of what the dissolving is doing as it is taking place. So in a molecule of salt, or not a molecule, but a chunk of salt, you're going to have your ions that are just going to kind of be all stacked together with your sodium ions surrounded by chlorine ions, your chlorine ions surrounded by the sodium ions. So what happens is you're going to put it in the water, and if you remember our discussion of polar covalent bonds, you'll remember that in a water molecule, you've got covalent bonds between your oxygen and your hydrogen because they each want to obey the octet rule, and in order to do that, they're sharing electrons in order to make that happen. But because the electronegativities are different, they don't share the electrons equally, and the oxygen tends to pull the shared electrons toward itself more than the hydrogen is able to. So what that means is that we have a partial negative charge up here on the oxygen, and we have partial positive charges down here on the hydrogen. Okay, we've talked about all that already. So when you're in solution, when you put salt into water, the water molecules are all moving around because it's the liquid state, and they start running into this chunk of salt. And eventually the impact starts causing the ions to break off a little piece at a time. Okay, so what happens is that, let's say that this, I've got water molecules banging into this chloride ion from all directions. So the chloride ion breaks off and it's down here like this. Then, because of the attractive forces between the negative charge on the chloride and the positive charges on the hydrogen as a part of the water molecules are going to surround the chloride ion and put it in solution that way. So I'm going to draw it this way with just Lewis dot structures, and you can see that the hydrogens are going to be close to the chlorine because the positive is going to be attracted to the negative. The same thing is going to happen over here. It's going to happen up on the top, so the hydrogen is going to be the side that is oriented towards the chlorine, like this. And while I can only draw it in 2 dimensions, you need to picture it in 3 dimensions. There's water molecules on the front, there's water molecules back behind the board that are also going to be attracted to that negative chloride ion, okay? So then, once you've got that chloride ion surrounded by water molecules, the water molecules are going to continue to bang into this particle of salt. You'll break off a sodium ion, and in this case, since this has a positive charge, this is going to orient the water molecules around it the opposite direction that they were here. So here, you're going to have your oxygens that are going to want to be close to the sodium ion as opposed to the hydrogens, again, because your opposite charges are going to attract. And just like I said before, you want to think that, okay, this isn't just in 2 dimensions, it's actually in 3 dimensions, so that the sodium ion is going to be completely surrounded by water molecules, okay? So this is how the process of dissolving takes place, where the positive and negative charges between the ions and the partial positive and negative charges on the water molecules are attracting one another and pulling the salt into solution, okay? Now, how do we know whether something is going to split apart into ions or not? Because things like sugar dissolve in water, but sugar isn't ionic. He talks in the book, and again shows you some diagrams in there, how you can have some polar molecules that have a positive and a negative end to them. And so the negative ends of the molecule that you're trying to dissolve will attract to the positive ends of the water and vice versa. But how are we going to know if it's going to attract, if it's going to conduct electricity or not? Well, as we discussed before, in order to conduct electricity, you have to have ions present. So when I analyze what I actually have that I'm trying to dissolve, the easiest way to tell if it's going to make ions is if you have a metal and a non-metal bonded together in an ionic bond. So something like calcium fluoride is going to make ions when it breaks apart in solution. Well, what's that going to break apart into? Well, in this case, you're going to have a calcium ion with a positive 2 charge, and you're going to have 2 fluoride ions, each with a negative 1 charge. We're just going to break it apart into its ions. So this one's easy to tell. A metal and a non-metal is going to be an ionic compound. It will conduct electricity. Something like barium nitrate, you memorized a list of polyatomic ions. Don't let that slide away from you just because the test is over with. You do still need to remember those polyatomic ions. We're going to continue using them. So the barium nitrate, the barium is a metal. You should recognize the nitrate as an ion. So when this breaks apart into ions, you're going to have a barium ion with a positive 2 charge, and you're going to have 2 nitrate ions, each with a negative 1 charge. Okay? When you get into something like this, there is no metal present. And so probably the majority of the time, this is not going to break into ions. C6H12O6 is glucose. You probably remember studying that in biology. It's the simple sugar that plants will make in photosynthesis. If you have this in a solid form, it will dissolve in water, but it does not break into ions. It will dissolve, but it won't ionize. So a solution of these two, or of each one of these, will conduct electricity. A solution of glucose will not conduct electricity because there are no ions present, even though it will dissolve. This is ethanol. And again, you can see carbon, hydrogen, oxygen, they're all nonmetals. And so it's not going to break apart into ions. And so again, while it will dissolve in water, because it is polar, if you would draw out the Lewis dot structure, you would be able to figure out that this is a polar molecule, so it will dissolve in water, but it will not ionize, it won't break into ions, so this will not conduct electricity either. Once in a while though, you have to watch this and be careful. You are going to have a compound that has all nonmetals in it, like this one does. Everything here, nitrogen, hydrogen, sulfur, oxygen, these are all nonmetals, but here you should recognize something different. Here you should recognize this NH4 as being an ammonium ion and the sulfate as being a sulfate ion. So this, if you put ammonium sulfate into water, this will break apart into ions, and specifically it will break apart into 2 ammonium ions and 1 sulfate ion with a negative 2 charge on it. So this one will conduct electricity. So in your assignment today, you're going to be practicing figuring out whether different compounds, if they are dissolved in water, whether they're going to ionize, what they're going to break into, and whether or not they're going to conduct electricity.